Okay, good morning. We are on to lecture number 6 in the first module in this course on advanced structural analysis. We are reviewing the basic structural analysis part 1. We are at the concluding section of this part where we are reviewing work and energy methods. In fact, work methods we finished, energy methods we had started in the last session. We are referring to this book on structural analysis, and this portion is covered in part 3 of that book. If you recall, we ended the last session with the theorem, a popular theorem in energy methods, which says that the external work on a structure is equal to the internal strain energy. Now, the use of that theorem is limited to finding unknown displacements. Why is it limited? It is not versatile. What is the limitation in the use of that theorem?
Cause, and there should be a cause effect.
In all energy methods there should be a cause effect. No, that is implicit in most of the energy methods. The limitation is you can find a displacement only under a load location, and there must be only one load. Do you understand? We'll demonstrate that with this problem of looking at shear deformation. So let's look at this cantilever beam subject to a concentrated load P at the free end B, and let that deflection be dB. What's the answer for dB? Normal PL cubed by 3EI. You can prove it by conjugate beam. PL cubed by 3EI, but that is not a complete answer. Why not?
Because it doesn't include shear deformation.
Because it doesn't include shear deformation. So we will see closely at how the shear deformation affects. So you can see the shear force diagram is shows a constant shear force P, and the bending moment diagram, in this case it is a sagging bending moment diagram, linearly varying. And if you want to find the strain energy in the system, it is easy. You can use that formula, but now we will include shear strain energy as well, right. So if you look carefully, this part where we multiply the bending moment diagram by itself is the part that comes from flexural strain energy, and this part is the part that comes from shear strain energy. And so the total energy would be given by this expression, where you both have flexural rigidity and shear rigidity Ga dash. Now this we can equate to what? This is strain energy in the system.
Net internal.
The total external work, the real work, which is equal to? No, P times dB is virtual work. What is the full expression for real work? Half P dB, because there is a cause effect relationship. We assume gradual loading, linear elastic behavior, and this is how we invoke the theorem of this theorem, which says that the external work is equal to the strain energy. Mind you, if in that cantilever beam I had put a uniformly distributed load, I would not be able to find the deflection using this theorem, right, because then there will be many displacements. In any case, look at this, you will find that the deflection now is PL cubed by 3EI plus an additional factor PL by Ga dash, which reflects the deflection that comes from shear. An interesting point to note here is you will find that the deflection that comes from flexure varies with the cube of the length, whereas the deflection that comes from shear is linearly dependent on length, right. And this is because the shear force is constant and the bending moment varies linearly. Let us try to see what is the relative contribution of shear deflection. So we can take the ratio of deflection due to shear divided by total deflection, and you can get this expression which can be written in this form: dB shear by dB is equal to this. Let us define a parameter C, which is L squared by 3 into G by E. G by E is a ratio that depends on Poisson's ratio, and A dash by I. Now let us take a simple example of a rectangular section, and for a rectangular section and for a material like steel where Poisson's ratio is 0.3, that expression for C will reduce to something like 1.282 into L by D the whole square. So you will find that L by D, span to overall depth ratio, actually dictates the contribution of shear deformations to the overall deflection, to the overall energy. And if you want to look at some practical examples, if the span by depth ratio is high, as it normally is, which is what makes the beam a skeletal element, a line element, you will find that the ratio of shear deflection to total deflection is low, negligibly low. 0.0035 is very low, it is 0.35%. If the span by depth ratio is 10, it is double that, 0.7%, and if it is 5, which is an intermediate beam, it is 3%. If it is 2.5, it is 11.1%, but if it is 1, which is the span is equal to the depth, it is as high as 43.82%. This is the reason why when you deal with, say, short squat shear walls, you really have to include the shear stiffness, but if you have tall slender shear walls, then you can treat it as a flexural element. So for normal beams you can ignore shear deformations, you will not have an error more than 1%, but for deep beams you can have very high errors. We now come to energy methods proper, and there is a term invoked in energy methods called load potential energy, and it is a concept which you need to understand. It is given here: the external work done by the force of gravity uses up a potential energy called gravitational potential energy, which is path independent and has nothing to do with the elastic behavior of structures. Every body subject to the force of gravity has the potential to do work, and that is gravitational potential energy. But we can extend this concept to all kinds of external forces acting on a structure, not necessarily due to gravity, and so we can talk of a load potential energy. Work is done when these forces undergo displacements, in which process their potential gets used up, and for this reason, because the energy gets used up, we associate a negative sign with this kind of work product, and it is nothing but the external work product with a negative sign. So the definition is very clear: load potential energy. That means we are converting the work done by the external forces, but it is not a real work. If it were to be real work, you would attach a constant like half. This is virtual work, and we give it a negative sign, and we give it the label load potential energy. Now if you have a system, a structure, where you have external forces and you have internal energy, you can add up all the energy, sum it all up, and call it total potential energy, defined as pi, capital letter pi, equal to capital U plus capital V. U is internal energy, strain energy, which is recoverable, and V is load potential energy. Mind you, U is always positive, U can never be negative, and V is negative. Is it clear? So we really don't, we actually talk about the changes in capital pi, and whether it changes or not we will see in the next slide. we can also define a complementary total potential energy where we put a star, an asterisk. So, pi star will be u star plus v. Okay. Now, if you are dealing with a linear elastic system, u will be equal to u star, and so pi will be equal to pi star. Now, so we have two broad sets of theorems, one related to total potential energy, another related to complementary total potential energy, in much the same way as in using the principle of virtual work. You had two broad principles, principle of virtual displacements and principle of virtual forces. So, you will find there is a strong correlation between these principles. The principle of virtual displacements is linked to the principle of stationary total potential energy. We will come to this in a moment. So, this is one set of relationships where we look at the displacement field, they are called energy methods based on the displacement field, and we imagine that displacement field is modified ever so slightly. You give a perturbation to the displacement field and then you see what happens. You get another set of principles when you disturb the force field without disturbing the equilibrium in that field, and those principles are related to complementary potential energy, and you have a 1:1 relationship with the principle of virtual forces. This is a kind of a big map, an integral map where you see all the energy methods, and we will take a quick overview of these principles. We will first look at the displacement based energy methods. So, let us take for example a truss, and to generalize, let us assume that all the elements are elastic but not necessarily linearly elastic. So, if the elements exhibit non-linear elastic material behavior, then the loads, the deflections that happen at the joint locations, the so called external component of the force field and displacement field, will also show a corresponding non-linear behavior. So, let us take any coordinate j in the truss, it could be a vertical coordinate or a horizontal coordinate, and let us just see how that relationship between fj and dj changes as you increase the loads from 0 to the maximum value. And let us say that at some point it is stabilized and you have equilibrium, and we imagine that we gave a small perturbation to the displacement field, still maintaining compatibility, which means let us say d1 we change by a very small quantity, say 0.1%, either positive or negative. Similarly, d2 I do by some other percentage, d3 and so on. So, I do this in my mind, it is all imaginary, and we are going to invoke variational principles to prove this theorem. And so, you will see if you look at the jth coordinate, if I give a small perturbation delta dj, which you see here, then there is a small change in the load potential energy, because fj is not changing, you are not disturbing the loads. So, you will find that the external work or virtual work is fj delta dj, and if you give it a negative sign, it becomes the increment or the variation in the load potential energy. Now, if you sum up this over all the joint locations, you get the total load potential energy variation. Is it clear? And this must be equal to the corresponding internal virtual work, right, internal virtual work. So, the principle of virtual work says sigma fj delta dj must be equal to sigma ni delta ei, where the ni ei graph, the nonlinear picture may look like this, and that incremental strain energy is delta ui, right. So, first we look at the principle of virtual work. It says sigma fj delta dj is equal to sigma ni delta ei. Clear? Now we bring in the concept of load potential energy. We see the term on the left hand side is minus delta V and the term on the right side is delta U. When you bring them both on the same side, you get delta V plus U, which we have defined as delta pi. So what do you conclude from this small proof? You get a theorem. What does the theorem say? What does it say?
The total stationary potential energy is constant.
Right. So, and it's a statement of equilibrium really. So the principle of stationary total potential energy, PSTPE, states that when the displacement field in a loaded elastic structure is given a small and arbitrary perturbation, maintaining compatibility and without disturbing the associated force field, then the first variation delta pi, first variation of the total potential energy is equal to 0 if the forces are in a state of static equilibrium. Is it clear? So this reminds you of which work principle? It goes back to Bernoulli. This was his idea of principle of virtual work, more correctly called the principle of virtual displacements. Is it clear? So it's the same thing expressed in an energy format, and it basically establishes equilibrium in the force field, and you can find an unknown force component in that force field. Now the alternative form of this same principle is more popular. So let us say you have some independent displacement parameters, I will give you an example, which usually is equal to the degree of freedom in that system, and let us call them d1, d2, d3 etc. Then you can always write pi, you can always write u and v in terms of these independent displacements, and so you can write an expression delta pi as a function of delta d1, delta d2 etc. equal to 0. Now if they are really independent, then you can invoke this chain rule, right? The chain rule says that delta pi can be written as delta pi by delta d1 into delta d1 plus this plus that equals 0. And what does the chain rule say? If this condition has to be satisfied, each one of these terms should be 0 because delta d1 etc. are independent and arbitrary, right? And if you do that, that one equation multiplies into large number of equations, as many as there are degrees of freedom, and you shift from a variational calculus formulation to a differential, partial differential equation. So dou pi by dou dj is equal to 0 for j equal to 1 to n. So this is a better form for engineers to work with. And in this form, that same theorem says that when pi is expressed as a function of independent displacements d1, d2 etc. in a compatible displacement field, it must be, if it is must be rendered stationary with the partial derivative of pi with respect to every dj being equal to 0, and this happens if the associated force field is to be in a state of static equilibrium. Now the word stationary in calculus refers to a point of inflection, okay. It could also be a maximum point, it could also be a minimum point of the function for which you are taking the partial derivative. Now it can be proved if you have a linear elastic stable structure, then the stationary point refers to a point of minimum energy. So in that form it is more popularly known as the principle of minimum total potential energy, right? It's PMTP. Let us just demonstrate how do you do this. Take that same cantilever beam problem, let us derive an expression for bending moment not using the conventional equilibrium, direct equilibrium, but we go the long winded way through energy formulation, assuming a displacement profile and then figuring out what would be an expression for bending moment. Now let us do it as exactly as possible. We know very well that the deflection function should be a cubic function, right? Why should it be a cubic function?
Unit it is
Concentrated.
it's a
Because
concentrated
you are dealing with a concentrated load and hence a linearly varying bending moment, and if the bending moment varies linearly, the curvature varies linearly, whereby the slope will vary quadratically and the deflection would vary cubically, right. So let us take a polynomial cubic equation C0 plus C1x plus C2x squared plus C3x cubed, and if we invoke the boundary conditions and you have kinematic boundary conditions at x equal to 0, the deflection and slope are 0, and that equation will simplify to this equation, which is a clean cubic equation having two components, one involving a square term and another involving a cube term, and constants d1 and d2, which are now the independent parameters we are looking for, right. So we can say the deflection at the free end is d1 plus d2, because when you put x equal to L, that equation degenerates to this one. Now you can also derive an expression for curvature by taking the second derivative of delta x, and using this expression for curvature you can get an expression for strain energy, right. Is it clear? We have done this earlier, so I am not going in depth. You have second derivative which is assumed to be equal to the curvature, and from curvature you can get strain energy, and when you integrate this, I am going fast over this, you get that expression. Now you look at total potential energy, which is V equal to minus P dB. You substitute dB as d1 plus d2, and in the next step you can invoke this principle of minimum potential energy and take you got two equations, and dou pi by dou d1 equals 0 and dou pi by dou d2 equals 0. You can solve them simultaneously and you get exact values of d1 and d2, and you get back the expression that we had derived earlier for deflection, including, of course there we had including shear deformations, but without shear deformations you get PL cube by 3EI. Once you have the expression for delta x, because if you look here in this expression d1 and d2 were unknown, once we invoked this theorem we could get the values of d1 and d2. You plug in these values into that equation, you get the exact equation for the deflection function, and you know that from this you get the curvature, and from the curvature by multiplying with EI you get the bending moment. So, and that bending moment equation P into L minus X is 100% correct, you know that, you can check it out through equilibrium. So this is an alternative way of establishing equilibrium, not particularly useful in this example, which we could have solved more easily using direct equilibrium. Another common example is to find assume a deflection shape which satisfies compatibility to some extent. So take a simply supported beam, assume a series function which satisfies compatibility, let us say a sinusoidal series, and let the midspan deflection be d. So d can be expressed as a function of many independent other functions d1, d2, d3 etc., and the definition of stiffness would be k is equal to p by d, where p is the concentrated load acting at the midspan. If you repeat this exercise, find the curvature, find the strain energy, write the expression for total potential energy, and if you take one term for example and assume that the higher order terms are not important, you invoke this principle, you actually get an expression for deflection and thereby for stiffness which is quite close to the exact expression. What is the exact expression? 48 EI by L cubed. You have got a reasonably good expression. So these are ways of using this principle, but a more popular use of this is Castigliano's theorem, which can be derived from this principle. So pi can be written as u plus v, v is written as minus sigma fj dj, and when you invoke the principle of minimum total potential energy, you will find that this will reduce to dou u by dou dj is equal to fj, right, and in this form it is known as Castigliano's theorem part 1, and it is similar to the principle of virtual displacement. This theorem states that if the strain energy u in an elastic structure, mind you we are not saying it should be linearly elastic, subjected to a system of external forces in static equilibrium, can be expressed as a function of independent displacements d1 to dn satisfying compatibility, then the partial derivative of u with respect to every dj will be equal to the value of the conjugate force fj. It is actually the same as the earlier principle expressed in another form, and you can use this to actually derive stiffness coefficients. You can prove that Kij is the second mixed partial derivative of the strain energy with respect to di and dj. Okay, this proof follows from, so you get one from Castigliano's theorem, which starts with this expression dou u by dou dj is equal to fj. You can derive an expression for Kij, which is dou squared u by dou di dou dj, and let us demonstrate this with a simple example. Here is a 2-bar truss, it has 2 degrees of freedom. That joint B can move horizontally, it can move vertically, and the elongations E1 and E2 can be expressed in terms of D1 and D2. You can easily prove this. E1 is equal to D2 and E2 is equal to D2 cos 30 degrees. Okay. This is what you do. The first diagram is what you do when you allow only D1 to occur and D2 is restrained. The second shape is when you allow D2 to occur with D1 restrained. You can work out the relationships between bar elongations and the deflections, and you can write them in a form E1 and E2 are related to D1 and D2 in that form. So if someone gives you D1 and D2, you get E1 and E2. Now you can write an expression for strain energy. How do you write the strain energy expression? What is the strain energy for a spring element? Half k into
displacement
elongation square, right? So you have elongations here, so it is half k, let us say both the elements have the same stiffness k naught, half k naught into E1 squared plus half k naught into E2 squared. E1 is equal to D1 plus root 3 by 2 D2, and E2 is equal to minus half D2. If you plug in those values, you can write an expression for u in terms of D1 and D2. Is it clear? I am going fast, you can verify this. Now if you take the partial derivative of D1 and D2, you get 2 expressions, and if you go to the fundamental definition of stiffness matrix, stiffness coefficient Kij, dou squared u by dou D1 dou D2, you can actually derive values of K11, K22, etc. in this manner. Now this is the hard way of doing it. We will be studying matrix methods where you do not need to do all this, you can generate it automatically, okay, but this is the original background to that derivation. You can also use it to find unknown bar forces, but for manual use usually we would do finding unknown forces directly, okay. You would not be using Castigliano's first theorem because it is more difficult. The real use of these theorems, so I am skipping this, real use of these theorems are to find unknown displacements, and for which you need to shift from this set of theorems. You notice here we finished the use of displacement based theorems. You can use it to set up equilibrium equations, dou pi by dou dj equal to 0. You can use it to find unknown forces, that is Castigliano's first theorem, dou u by dou dj equal to fj. You can also use it to find stiffness coefficients kij. Is it clear? So these are powerful uses, at least theory wise you should be familiar with these terms. Now we will look at the force field, which is related to principle of virtual forces. So you have corresponding principles. So corresponding to delta pi equal to 0, you have delta pi star equal to 0. So you would call that theorem the principle of stationary total complementary potential energy, and you see a parallel. You use this to find some unknown displacements in the displacement field. So instead of setting up equilibrium equations, you now set up compatibility equations. Instead of finding unknown forces, you find unknown displacements. Instead of finding stiffness coefficients, you find flexibility coefficients. You are doing a similar exercise and you see a beautiful symmetry in these relationships, and you can do the same thing using work methods without getting into energy, and that would be a use of the principle of virtual forces. So can you see this map? With practice you will be familiar with these different approaches. So now I will go fast. You are familiar with the way of deriving these theorems. Here you go back to that truss, and instead of disturbing the displacement field, you disturb the force field. You increment those forces positively or negatively by a very small component, and you invoke the principle of virtual work, and you will find that now delta V plus delta u star, which is delta pi star, is equal to 0. You can prove this in the same way. Okay, so there is no need to explain this further. So you have the external incremental change in work and the change in strain energy. So the principle in this form states that when the force field in a loaded elastic structure is given a small and arbitrary perturbation, maintaining equilibrium and without disturbing the associated displacement field, then the first variation of the total complementary potential energy is equal to 0 if the displacements satisfy compatibility. If you write this equation side by side with the earlier equation, which is the principle of stationary total potential energy, you will find many similarities and differences. The format is the same, but there you are disturbing the displacement field. Here you are disturbing the
Force field.
When you are disturbing the displacement field there, you are not changing the forces. When you are disturbing the force field here, you are not changing the displacement. So that is important to note. It is something you do in your mind. It is arbitrary and it is of very small value, and the cause that you refer to here is perturbation and the effect is variation. Those are the terms used. Now in the first one, when you disturb the displacement field, you are maintaining compatibility. Here when you are disturbing the force field, you are maintaining equilibrium. And when you find the first variation delta pi here, delta pi equal to 0 is a statement that establishes equilibrium in the force field although you disturbed the displacement field, whereas here delta pi star equal to 0 is a statement of compatibility which you get although you disturbed the force field. So there is a symmetry in these relationships. An expression of compatibility, you can go through the same procedure and you can find the alternative form which reduces to dou pi star by dou fj equal to 0. Earlier it was dou pi by dou dj equal to 0, and that one equation, that is the first variation of pi star equal to 0, now multiplies into n number of equations depending on the number of independent forces that you get. Okay. So in this alternative form, it states that the total complementary potential energy pi star in a loaded elastic structure expressed as a function of n independent forces F1 to Fn in a statically admissible force field, that is force field which satisfies equilibrium, must be rendered stationary with the partial derivative of pi star with respect to every Fj being equal to 0 if the associated displacement field is to satisfy compatibility. Here again, if you are dealing with a stable linear elastic structure, the condition of stationarity reduces to a condition of minimal value of the function here, which is pi star. So in this form it is called PMTCP, that is principle of minimum total complementary potential energy, a mouthful of words, but it is the concept that you need to remember. One simple demonstration, again let us take a cantilever beam, but this time it is different. You have many loads acting, you have one load, let us take load P, but you want to find the slope and deflection at some arbitrary location x. Okay. Now in this theorem you have to impose, if you want to find d1 and d2, d1 is the slope at x and d2 is the deflection at x, you have to introduce imaginary corresponding conjugate forces F1 and F2 and later put them equal to 0, because that is how you generate the equations. You are familiar with Castigliano's theorem. So write down the bending moment expression. You can separate out the real one caused by P, which is a straight line, and the one caused by imaginary F1 and F2, which is also a straight line but not starting, not yeah, it is exactly as shown, and you can write down the value. So M at any location xi has two forms. You have to break it up into two parts, one up to x and one beyond x, and beyond x you will find F1 and F2 do not have a role to play because there is no bending moment caused by F1 and F2. So you have got this expression for bending moment at any location xi, and you can expand this ignoring shear deformations, write an expression for u star, okay, that can be generated easily. This is u star, the full form of u star. Now this u star is a function of not only P but F1 and F2. Now you invoke the theorem, load potential energy pi star, what is V? V is minus P into the total deflection under the load plus the deflections caused by the imaginary F1 and F2, right. So you get that expression and invoke the theorem dou pi star by dou F1 equal to 0, and when you invoke this expression, when you take the final form you should insert the values of F1 and F2 equal to 0. Similarly you take the second equation dou pi star by dou F2 equals 0, you get the values of d1 and d2, you get the slope and deflection using this energy formulation. You can do the same thing using Castigliano's theorem part 2. Here again you can prove using a similar procedure dou u star by dou Fj is equal to dj for 1 to n, and here you can take advantage of the fact that u is equal to u star for linear elastic behavior, and so for beams you get that expression. Can you say something about these expressions? Have you encountered these expressions earlier in a different form? For beams it takes this form for right. If you recall the unit load method, which is the principle of virtual forces, there also we had 1 into dj equal to these quantities, right. This is the internal work. Now the similarity is everything is same except this expression comes in. What is dm by dfj? It is the small mj that we refer to that. It is the bending moment caused by Fj equal to 1. So if you look at it carefully, they are all the same. They are only different ways of approaching the same problem. You are doing the same kind of integration, or you can do area multiplication, whether it is a beam or a truss. So in summary, this theorem in its part 2 says if the complementary strain energy u star in an elastic structure with a given kinematically admissible displacement field is expressed as a function of n independent external forces F1 to Fn satisfying equilibrium, then the partial derivative of u star with respect to every Fj will be equal to the value of the conjugate displacement dj. If the behavior is linear elastic, u star can be replaced by the strain energy function u. Here again you can expand d in terms of flexibility coefficients, and like in the earlier case you can use energy methods to get an expression for flexibility coefficient. Fij is the mixed partial derivative of u star with respect to Fi and Fj. So the similarity is now complete with stiffness coefficient. Now there is a special application of this theorem, it is called the theorem of least work, to solve statically indeterminate structures. Let us say you have a continuous beam and you want to choose the redundant reactions as your redundants. So x1 to xj, dou u star to dou xj actually denotes what? By Castigliano's theorem it denotes the displacement at those support locations. Now those supports do not move, so those displacements are 0, and so you can also interpret this as a minimization of strain energy. We will discuss this shortly, that is called the theorem of least work, but let us demonstrate this with a problem. You remember we did this problem finding d1 and d2 using unit load method, right? Here let us make it more complex by including axial deformations and shear deformations. I will go through it fast. You can find it using Castigliano's theorem. First find the deflections due to bending. So you have a bending moment diagram, and to find d1 you apply F1 equal to 1, you get the unit load bending moment diagram M1. To find d2 you find M2. These are nothing but actually dou capital M divided by dou F1 and dou F2, and so you can work out the same method, it resembles the unit load method, and you can find that the deflection caused by bending is 5.61 at point 1, and if you want, and at d2 it is something, then you can also find deflections caused by shear, okay, using the similar expressions, and at the end of the day we are interested in total values. You will find that the total deflection d1 and d2 is 5.64 and 9.34 mm downward and to the right, and those additional terms that we have cut off here are terms that come from shear and axial, and you will see that they are actually negligible. So there is again another proof why we can ignore shear deformations and axial deformations in normal frames which are well proportioned. Earlier we said that the energy caused by shear and energy caused by axial forces is negligible. Now we are actually saying not just the energy, it is also the deflection. So do not bother, make your life easier. When you see a frame, worry only about bending, flexural strain energy. When you see a beam, do that unless the beam is deep. When you see a truss, only axial strain energy. So you can use it to find truss deflections, same method, a little complicated, you have many members here, you given the area of cross section of each member, given modulus of velocity, you can use Castigliano's theorem to invoke deflections at any points of your interest. First you need the axial flexibilities of all the members, and then invoke this equation and you can prove this. These are exercises that you need to do, we are just reviewing something that you have already learnt. You can do it in a neat tabular format and get the answers. You can also find flexibility coefficients just the way we found the stiffness coefficients. So it is similar once you get the hang of it. Earlier what did we do? We wrote a relationship between E1 E2 and D1 D2. Now we write a relationship using equilibrium between N1 N2 and F1 F2. and we will study in matrix methods that this coefficient matrix you get here is actually the transpose of the other matrix which we got in displacement method. We will give a formal proof for that later. Now you calculate, you write an expression for complementary strain energy, and you must remember the Castigliano's theorem simplified everything, because it got rid of load potential energy, it got rid of total potential energy, and so you have only strain energy and complementary strain energy. Many students when they study structural analysis remember only that, but it is good to remember the background which includes load potential energy term. So you can invoke this in this example, and exactly similar operation, and you can find an expression for flexibility matrix. And if you go back to the same problem we did earlier, you will find that this matrix is related to the K matrix. How? One is the inverse of the other, you can prove it. We will end with this theorem of least work, which I have already explained. For a statically indeterminate structure, dou u star by dou xj is equal to dj. In general, except when support movements are involved, dj is 0. This is even true for internal indeterminacy. So you can give this an interpretation. When you say dou u star by dou xj equal to 0, you can view it as a minimization of complementary strain energy. So the expression goes this way: the theorem of least work states that of all the possible values that the redundants in a statically indeterminate and linearly elastic structure can assume, the true solutions ensuring compatibility in the displacement field correspond to the condition of minimum complementary strain energy u star, or because it is linear elastic you can say minimum strain energy u, because both these terms are equal. Simple demonstration which I asked you in an earlier class. Let us say you want to solve this problem and the support reaction in the middle is treated as the unknown x. You remember I said every student in this class can give his own value of x, and you can compute strain energy, and if you actually compute strain energy, which means you have to integrate the bending moment diagram, take the square of it and so on, you will find that for any value of x you can get a complementary strain energy, and you can even assume foolish values of x which go negative, it is not going to be negative, and you will find that if you plot x, every value of x will give you other reactions which are statically admissible. You will find that you will get some strain energy, but that strain energy value will be high. The exact solution, the correct solution is one for which the strain energy is minimum. And you can prove this. You can write an expression for m bending moment at any location, write an expression for u star, and take the derivative, and you can prove. There are a series of steps you can get the final answer. So with this we have completed a review of structural analysis 1. In the next sessions we will cover 2, which first half will cover force methods including theorem of least work. The second half of that will cover displacement methods, which you have not yet studied.